In this video, we're studying the motion of a particle that's moving on a spiral trajectory at constant angular velocity, but increasing radius. So the position vector for this particle is given up here by r of t equals 0.1 t cosine pi over 2 t I hat, and then a similar term, 0.1 t sine pi over 2 t j hat. So the way to look at this is that we have an object moving with constant angular velocity of pi over 2 radians per second. So we have that cosine pi over 2t and sine pi over 2t for the I hat and j hat terms, but out in front of that is an increasing radius of 0.1 t. So the radius is going to start at 0 and then increase linearly from there. Now what we're trying to find in this problem is actually just the speed of the particle at the given time of 1 second. So if we run an animation where the velocity vector is shown attached to the particle, that velocity vector is always tangent to the trajectory as usual, but we see that it's growing in magnitude as the particle moves farther from the center. So this is significantly different from uniform circular motion. Our speed must be increasing because the particle is constantly moving farther from the center, but always maintaining that same angular velocity of pi over 2 radians per second. So let's stop the animation at the moment of interest, in other words, t equals 1 second, where the angle is pi over 2. To get the speed at this point, we just have to use the time derivative to find the velocity vector, and then we use the Pythagorean theorem to get the magnitude of the velocity vector, and we're done. So we get started with the derivative of the x component here. And this is going to require the product rule because we have a product of two functions of time. We have that 0.1 t, and then we have the cosine part. So taking the derivative of the 0.1 t, we just get 0.1, and we leave the second function alone, so 0.1 cosine pi over 2t. And then in our second term, we have to leave the first function alone, that's 0.1 t, but multiply it by the derivative of the second function. Well, the derivative of cosine is negative, so I'm going to put a minus sign in here. And I do have to use the chain rule on the cosine of pi over 2t, so that produces a factor of pi over 2. So I end up with a 0.1 times pi over 2 times t, again that function was left alone, times the sine of pi over 2t, and that's all the coefficient of I hat. Then we look at our j hat component, and it's a similar thing. I have to use the product rule and the chain rule. My first term is going to be 0.1 sine pi over 2t, and then my second term gets an extra factor of pi over 2 because of the chain rule, so 0.1 times pi over 2t times the cosine of pi over 2t, and that's all the coefficient of j hat. So now we're studying this moment in time at t equals 1 second. So I want to evaluate the velocity vector at t equals 1. And I set this problem up so that the special angles would make things simplify really nicely. If I plug in 1 for t, that means the angle in all these trig functions is just pi over 2. And the cosine of pi over 2, that's 0. And the sine of pi over 2, that's just 1. So making all those replacements, I just get negative 0.1 times pi over 2. Also replacing the t with a 1 right there. That's our coefficient of I hat. And then the only survivor in the j hat term is just a 0.1, so I have 0.1 j hat. Now my intention when I wrote this problem was to just get a decimal approximation on the speed. So we aren't going to worry about any algebraic manipulations here. I just need to apply the Pythagorean theorem. And my x component has a magnitude of 0.1 times pi over 2, or you could call that pi over 20 if you want. And we're going to square that. And then my y component is 0.1, and I have to square that. And we add them together and take the square root of the sum of the squares. And when I run the numbers on this to our usual 3 significant digits, I get 0.186 meters per second. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.